Hey everyone, Morgan here. So we are looking at page 6 of the equilibrium outline. We're going to continue our conversation here about how to write an equilibrium constant. So as we look at this first reaction, I notice all 4 species are gases and they all have a coefficient of 1. Those are important concepts. So the K is going to equal the concentration of the SO2 times the concentration of the H2O divided by the concentration of SO3 times the concentration of H2. And you'll notice that each of the exponents is 1 because each of the coefficients is 1, and all the species are included because they are all gases. And this also illustrates nicely for us that an equilibrium constant is a ratio, products over reactants. All right, now for the next one. I have an equation here where every coefficient is different than a 1. So let's start off with the concentration of NO raised to the 4th power times the concentration of H2O raised to the 6th power divided by the concentration of NH3 raised to the 4th power, which is multiplied by the concentration of O2, which is raised to the 5th power. Again, a ratio, products to reactants, and when we went back and looked at that original definition set for equilibrium constants, I said that you had an algebraic expression, which this is most definitely an algebraic expression, and a ratio of products to reactants. All right, a little twist now. This next one, sulfur is a solid, so we will not include it. I have the concentration of H2SO3 divided by the concentration of H2S2O3, and that's it. For the one after that, only one product is a gas. None of the reactants are. So K is simply equal to the concentration of CO2. Now for the next one, my only product is a liquid, which I would not include. So I'm going to put a 1 up top. I cannot have a topless fraction. I need something in the numerator. So I'll just put a 1 divided by the concentration of CO multiplied by the concentration of H2 squared, because those are both gases. Also another one where there's a 1 up in the numerator, and the only thing downstairs in the denominator is going to be the SO2 raised to the 1st power. Then for this last example, it's the concentration of Mg2+ multiplied by the concentration of SO4 2-. Nothing downstairs because the MgSO4 is a solid. So I've got a numerator, nothing in the denominator, although it would not be wrong to put it all over a 1, but I typically don't do that. Okay, so what does the word constant mean? Constant's a number. Okay, and a constant in algebra, that's not changing. It's a number that stays the same. So the numeric values for these would stay the same. I think it's worth pointing out that it's also dependent upon temperature. They can change with temperature changes. All right. So, really important point here is that the size, the magnitude of KEQ tells us whether or not the products are favored or the reactants are favored. Basically, it tells us whether or not this reaction is spontaneous. This will look silly, but it drives the point home well. If KEQ is a large number, that means I have a lot of products and very little reactants. And generally, I would say that's a K that's greater than 1. And if KEQ is a small number, it's because I don't have much product but I've got lots of reactants, and that would generally mean a K that is less than 1. All right, so there's a little bit about how to write your KEQ values. Thanks for tuning in. This is Morgan, signing off.